to become as late as they were before COVID. Yeah. Okay, but let me get us started anyhow, and more will show up. So, any announcements, Domingos?
No, we don't have a talk schedule for next. Do we?
Well, we probably won't have another one this quarter because we're getting close to the end of the quarter.
Yeah, that's true.
We'll see. Okay, so hello everybody. It's a pleasure to introduce another relatively young speaker, Grant Rotskoff from the chemistry department at Stanford. Now he has a very nicely muddled career path here. So he's a newly hired assistant professor at Stanford, just started in the fall, but he got some sort of weird degree in mathematics from the University of Chicago. Maybe the rest of us get BSs, but he gets an SB. What's that, Grant?
I think it's just the way that Chicago orders the degree name.
But then he got a PhD in biophysics from Berkeley, and then was a fellow at the Courant Institute in New York. So he doesn't know if he's a scientist or a mathematician or what he is, right? And then he told me that recently he got some very good news. Well, I got a fright when he told me that he got a terminal faculty fellowship at Stanford. No, sorry, that's a Terman faculty fellowship. A terminal faculty fellowship wouldn't have been so good. Okay, so, but Grant's going to tell us about machine learning and using it for rare events and things like that in MD. So take it away, Grant.
Okay, so thanks so much for inviting me and for the introduction, which I think very relevantly pointed out, the fact that I do chemistry and biophysics, but I tend to think about these problems a bit like a mathematician. And what I want to tell you about today is, the way that some mathematical work that I've done on machine learning has informed the way I think it should be applied to problems in biophysics and chemistry. And so as you can see, the story is not wholly positive. It's prospects and perils of machine learning for rare events. So the first thing that I want to spend a little bit of time discussing is just, what are neural networks? What are they capable of representing? And how should we think about the relationship between the data, the number of parameters, and our ability to use these in a fashion that will generalize well, or will have good performance on data samples that are outside of a data set that we've trained on. So I want to raise a kind of provocative question, which I think is kind of interesting to consider. I like this plot a lot, so I understand that it's probably a bit hard to read. But basically what this is showing is the relationship between the amount of computational power used to train a model and as a function of time. And so, as you might know, models like AlphaGo 0 and AlphaZero have, state-of-the-art performance on very, very complex high-dimensional tasks, but they also require an absolutely extraordinary amount of computational power to optimize. And this trend, this exponential growth in the amount of resources we're willing to dedicate to training state-of-the-art models has been in place since about 2012. So for much of the so-called deep learning revolution, we've been seeing an exponential investment in the amount of computer resources we're willing to dedicate to training models. And so you could raise the question whether or not deep learning is actually doing something new and different from the types of approaches that we might have taken in the past, or whether we've simply just put more of our effort into it, and that it's not actually somehow fundamentally different from other computational techniques. So this plot comes from an OpenAI blog post. And it raises an interesting question, which people often refer to as the curse of dimensionality. So is there somehow an ability for neural networks to overcome the curse of dimensionality, which says that there is an exponential amount of, say, data required to learn a certain distribution in high dimension? And that's the question that, you know, I kind of want to focus on. Are neural networks better at representing high dimensional functions than other techniques that we know about? So in order to discuss this, I think it's useful to think about something that we all know from thinking about fitting functions with, for example, polynomial fits. So as a physicist, you know, you're trained to think that the right model is the one that has the minimal set of parameters to describe some phenomenon. This is something, you know, I think that we were all brought up with and internalized, and, you know, it's slowly disintegrating in in the modern perspective. So, you know, there's this notion that as I increase the capacity of a model, so this could be the number of parameters divided by the total amount of data, for example. So this is something that tells me about how many parameters I have relative to how much data I actually need to learn. Then, so the notation or the nomenclature that's used is risk, but this is the same as loss, right? This is like the test error will decrease as I train. So as I get a better model by increasing the number of parameters, I get a transient decrease in the test error. But then at some point, as I start to overfit, so this is the regime where I'm overfitting, I've trained the model so that I get a very accurate representation on the data set, but I have some sort of overfitting where, you know, I have some sort of issue with the polynomials that interpolate a set of data points that, you know, the tails go off to infinity and I get something catastrophically bad. So this is the picture, you know, that I was brought up with, and I, you know, thought was the case for a long time. But recently, you know, we've observed something that looks quite different from that. And this is sometimes called a double descent phenomenon. So in the modern era, the modern interpolating regime, what we see is something that looks quite different, which is that there still is this transient increase in the generalization error as I increase the number of parameters in a model. But once I go to, you know, this limit of very large neural networks, I mean, the alpha 0 models, for example, have literally billions of parameters. We enter a regime where we can interpolate the function, but we don't pay a price in the generalization error. The generalization error actually improves, and it improves even relative to the minimum of this classical regime. So as we increase the number of parameters, we end up in a regime where we can fit basically, you know, very complicated high-dimensional functions almost arbitrarily well. And this is something, you know, that you can see in experiments as well. So this is, of course, just a schematic picture of what's going on, but you can do experiments on real neural networks where you control the number of parameters per unit data. And what you see is that you have exactly this picture of things. So there's a region where you find this classical sweet spot where things perform well with a small number of parameters. You at some point start to overfit. So that's when the number of parameters is comparable to the amount of data, slightly larger than it. And then as you push yourself into this regime where you have many, many more parameters than data, something changes and you start to, you know, have this second descent on the curve of the error, and you end up with something where you actually start converging to a representation that is better than you ever would have achieved with a minimal model. So, you know, the takeaway from this, at least for me, is that overparameterization is not an empirically harmful effect. So, I think there still is some hesitancy about using neural networks with large numbers of parameters because people think of them as, you know, somehow sloppy, right? They're models that are not, you know, well determined enough to actually recapitulate the underlying data set. They're just, you know, they're so expressive that they're just learning things and overfitting. That's not the case. So if you have a large number of parameters, you don't overfit, and that's what this set of studies around this double descent phenomenon is really illustrating in a rigorous way. So that sort of picture has informed how I think about neural networks quite a bit, and where I think they're useful in physics and chemistry. So I want to talk just really briefly about some work that I did at the Courant Institute with Eric van den Eijden about the dynamics and trainability of neural networks as kind of motivation for understanding, what types of problems in chemistry I think neural networks are really useful for. So I want to consider the simplest possible model of a neural network and just think about, what we can say about the dynamics of it. So let's take a single hidden layer neural network, the minimal architecture that I would call a neural network. And this object is just a function, right? So it's some function that takes, an input x, which is in the space of my data, and some set of parameters theta. And I represent this function just as a sum over a bunch of neurons. So my neurons are these phi functions. And I'm just going to write this as a sum normalized by 1 over n. So I get something order 1 in the end. And my target, I assume, is also a function. And this could be a very, very high dimensional function. This could be something super complicated. In a high dimensional space, like a reaction coordinate for a molecular system. And I have a bunch of parameters. And of course, we look at loss functions like the discrepancy between my neural network representation and this target function. So we measure this discrepancy on a data set and we minimize it. So that's the basic paradigm that gets used. You can change these loss functions slightly. You could make the architecture much more complicated, but most neural networks are trained using this basic paradigm. Okay, so what can we say about these types of representations and the limit that the number of parameters becomes very large? So this notion, which we call a mean field limit for reasons that will become clear in a second, is to take the number of parameters to be going to infinity. So we take this limit that n goes to infinity, and we just take that loss function from the previous slide and expand it. It's a quadratic, right? We can just expand it into 3 terms. There's one term that involves only the target function from that quadratic. That is a constant. It doesn't affect the optimization at all. It's just a shift. And then there are 2 terms that depend on the parameters directly. So the first is an average that involves the target function on the data set and my representation on the data set. And the second is something that involves only the representation on the data set. So the only reason to do this is that it makes you appreciate something about the neural network optimization problem that you might not otherwise see if you hadn't written it in this particular form, which is that this now looks like an interacting particle system. So this looks like an energy function for a bunch of particles. The particles are the thetas. So my parameters are playing the role of particles in this system. And that has a big advantage, one that I think many people here will be very familiar with, which is that, sometimes when you have a bunch of discrete objects that are interacting and you want to create a representation of their energy, it's much more convenient to look at the density rather than looking at the individual particles, right? So I don't want to be in a situation where I have to track the complicated dynamics of every particle in my system. Instead, it's much easier to work with the density itself. And so what we can do is we can take in this limit that the number of parameters becomes large, a limit where we just study the evolution of a density for the parameters mu, rather than studying the individual discrete evolution of every parameter itself. Okay, so what do you get from this perspective? Well, what you get is an analogy that allows you to write the gradient descent for the individual particles in terms of the evolution of this density of all of the particles together. So this is like trying to write down a Fokker-Planck equation for an interacting particle system. But instead of, having particles in three-dimensional space, I have parameters in whatever dimension the parameter space is. Okay, so you can start with the gradient descent equation for these particles. And then you can notice that this is now an evolution on an energy functional. And the functional itself has a simple form. It's just, instead of having the thetas here, I have replaced those thetas with an integral against this density. And the integral, so in terms of this density, this is a convex function. So I now have an energy functional which is convex, which already is a strong suggestion that you should expect some notion of convergence in this limit that the number of particles becomes very large. Is on convex functions, it's easy to minimize, right? It's a bowl-shaped function in the space of measures, and so you should be able to descend on that. And so you can write down a corresponding partial differential equation. This partial differential equation it's just like a Fokker-Planck equation. And it basically is telling me about the way in which this collective density for all of my particles evolves. And, this is just writing this as a descent dynamics in the space of measures, right? In the space of densities for my individual particles. So,
sorry, Grant.
Yeah.
Can I bug you?
Yeah, of course.
Well, first, aren't you assuming your training is, or maybe you're not assuming the your trained, your parameterized form is close? I guess you're not, right? Because you didn't do an expansion.
Yeah, so everything that I've written so far is exact. The only thing that I'm really assuming is that I have a single hidden layer network. So this is using an expansion of F in my neural network into a single hidden layer form. So I've kind of hidden some of the details here. You can write this. Okay, so in the interacting particle language, right, this is like a single body potential. And it's basically saying, put the neurons where you get good agreement with the target function. So right. It's basically pointing, all of my, so if you think of these as like vectors in some Hilbert space, right? It's saying point that vector in the right direction so that I get good agreement with the target function. These are like basis vectors aligning. And the second term is something that plays the role of an interaction term. And that interaction is repulsive. So you can check that this term is positive definite. And so you get something that actually spreads out the points. So it's kind of like you end up with an efficient type of interpolation where you're spreading the parameters in space so that they don't collapse all onto like a single point. So that picture emerges from assuming a single hidden layer network, but the expansion of the loss function. So if you have this quadratic loss function, then that expansion is exact. You could ask, can you do this for any convex loss function? And the answer is yes, but then you would need to make some approximations or you would have higher order terms. So this is kind of the simplest case in which that works.
But the other issue is, haven't you assumed something continuity for this mu, that your thetas are, as you get more and more of them, can be represented by some smooth distribution function, so some smooth envelope ultimately.
Yeah. Okay. So that is an amazingly prescient question. It's an incredibly good question. It's something that took actually us a long time to realize the importance of. So when you take this limit, right, you get some limiting object, but it doesn't need to be smooth, right? You could have infinite numbers of particles collapsing on points, right? That's fine too. So I'll come to that actually right now. Okay, so I'll explain why this is important in a second. So so this analogy, right? So we've written down an equation which is a PDE that looks like a gradient type dynamics from, for example, this is like I would call this a nonlinear Liouville equation, but it's a bit like a Fokker-Planck equation. So it's an equation that's telling you how the system, starting at some initial density, is going to evolve as a function of time under the gradient descent dynamics, how the whole density evolves. And there's a lot known about this type of equation from a literature that I learned about in doing this work, which is really in the mathematical analysis of partial differential equations. So there were a few people who realized that you could present all of this as a gradient flow in a certain metric space. And that metric space is one that actually appears in machine learning a lot. It's called a Wasserstein metric. And this is basically, it's an optimal transport distance. So it asks, how much work are you going to do to move one probability distribution into another? And so the dynamics that's written here is actually, this is a gradient flow. It's a gradient descent in a metric space where the metric is this thing, this measure for probability distances, which is the Wasserstein metric. And so you can make that explicit by rewriting the gradient descent equation as a proximal algorithm, where you're just writing this as a minimization with the metric made explicit. So this is the Wasserstein metric. And what's useful about relying on this mathematical analogy is that people have understood very well what conditions are required in order to reach a global minimizer in this type of dynamics, in this Wasserstein gradient flow. And the smoothness of the measure turns out to be a crucial property for that. So having a limiting density that is ultimately kind of spread out in some way turns out to be one of the most important aspects of proving that convergence. And so well, I told you that the energy functional is convex, and so you might expect that things are descending smoothly on that convex function. If you have this issue that Kieran was raising, where the density isn't smooth and things collapse into points, then you can end up with something where actually there are fixed points for the dynamics that are not minimizers. So this is kind of easy to see from the equation. So what do I mean by fixed point? So basically what I want is dt mu is equal to 0. Okay, that would be the condition under which the dynamic stops. And if dt mu is equal to 0, well, one way that can happen is that I can be at a minimizer. So I can be at something where grad v is equal to 0. So that's the kind of thing that I want. That's an energy minimizer. But you could also have that mu is equal to 0. This equation is linear in mu. So if mu becomes 0 almost everywhere, right? If everything kind of collapses onto a point and you don't have this sort of smooth coverage of the whole parameter space in the limit, then you could have that the dynamics just stops at a non-optimal point. So you need to have, okay, so this is kind of overkill terminology, right? You need to have what's called full support, which means that you have particles essentially everywhere, right? You have parameters everywhere in space in order to see convergence in the limit that t goes to infinity. So there are two things that you can do to help guarantee this in actual practical application where you have a finite number of neurons. So the first is that you want to always initialize things from a fairly broad distribution. So you want to choose your initial parameters from something that actually has pretty good coverage, pretty broad distribution. And then the other thing that's important is so there are very few neurons that satisfy the conditions that are required for global convergence in this framework. The one that actually seems to be the best is ReLU. So if you use rectified linear units, then you can guarantee global convergence. But if you use other standard types of neurons, then that might not be guaranteed. So if you use other neurons, there are other fancier things that you can do that involve some sort of non-local transport of the neurons. So, the neurons are evolving and the parameters are evolving according to gradient descent. That's a fundamentally local algorithm. Each parameter is descending on some energy based on its current position. But you can do other things to actually change the way in which these evolutions are occurring. And one of the ones that we've worked on a bit is to use birth-death algorithms. So basically doing a kind of evolutionary dynamics on the parameters themselves, where you kill and clone parameters according to their instantaneous fitness or their energy, really. So there are other things that you can do to help ensure convergence in this limit as well. Okay, so this is a bit of a mathematical framework just for thinking about the evolution of the parameters of a neural network and trying to understand some of their convergence properties and representation properties as well. And one thing that you haven't seen in any of the equations that I've shown is the dimensionality. And what that says is that there's a very weak dependence on the dimensionality for the convergence of neural networks. So, of course, there are caveats. You need to have a sufficient amount of data. You need to have a sufficient amount of training time, things of that nature. But what we find very generically is that given those conditions, so given a representative model, so a model with a large number of parameters and some data from a target distribution, you can learn very high dimensional functions. And you can check this really explicitly on models where you know the answer. So one thing that we've often done in order to verify these types of results is look at what are called student-teacher models, where we try to learn a neural network with a neural network. And basically what we find is that we can do this in essentially any number of dimensions, even when there's mismatch between the types of neurons in the network. So even in cases where it should require a very large number of neurons to learn the teacher model, we can still do this in a very large dimensional setting. So I mean, this is just a plot from d = 50, where we've used a student to learn a teacher model. And you can see from looking at a slice through any one of the dimensions, so this is just taking a slice through the function at some point, you can see that you recapitulate the function very well. And these other plots are just showing that you don't have like exploding parameters, which would be the case if you were to, do this in the classical statistical learning setting, where you're doing like a matrix inversion to compute linear coefficients to some kernel function. So that's something where, you end up with problems of what we call ill conditioning of matrices, and that leads to parameter values that blow up. But we don't see that in this case. So what tends to happen is that all of the neurons that are in the basin of attraction for values of the potential that are important for representing the target function, those neurons descend to the location in space where they should be, and the other ones basically go to zero. So you end up with something that by having good coverage of the parameter space is able to find the directions in which it's important to evolve in order to represent some target function, and the rest essentially don't contribute, and so they don't have a negative effect on the generalization error. And that's more or less the explanation for this double descent phenomenon. You have something where the overparameterization is explicitly not harmful because it's very easy for these neurons to represent zero. They just don't contribute if they're not in the basin of attraction for the parts of the potential function that comes from the loss that are necessary for a good representation. So this is a bit abstract, right? It's just saying we can represent high dimensional functions. And the reason that I got interested in this question in the first place was more because I wanted to use neural networks in the context of scientific computing, and I didn't really understand whether or not they actually do something meaningfully different from other techniques that we have available. And I think this is a very robust demonstration that they do. The one thing that we can really prove that neural networks can do that other methods cannot is exactly representing high dimensional functions. So this is kind of the crucial tool that neural networks offer that other techniques do not. And so when you think about whether or not you should use a neural network for some particular project, I think that that's a good test to ask yourself, like, do I actually have something that's high dimensional that I need to represent? Do I need to extract information from some very high dimensional input? And that's the context in which I have primarily tried to use neural networks. So I want to tell you about a couple of related problems that require representing high dimensional functions that are relevant to biophysics and chemistry. The main one, and one of the main focuses of my research, is what is often called the rare events problem. This is equivalent to reaction coordinate problem. And it is a quintessentially high dimensional problem. So a canonical example, at least in the biophysical context, is representing and describing transitions and reaction mechanisms between two conformations of a biological molecule. So what I've shown here is the subtle transition between the oxygenated and deoxygenated states of hemoglobin. And this is a concerted motion that involves the quaternary structure of a very large protein, which has, complicated allosteric interactions where the release and binding of oxygen are strongly affected by the state that the protein is in. And it's a complicated thing to describe in the context of computation because it relies very heavily on detailed simulations, so from molecular dynamics, for example, and those simulations are very costly, especially since the transition time is extremely long relative to the times that we can simulate. So we have this fundamental constraint in molecular dynamics where the oscillations of the hydrogen bond are sufficiently fast that we can only take time steps in the femtosecond regime. Many biological processes and transitions in some large and complex proteins take on the order of seconds. And I don't have computers powerful enough to do 10 to the 15 time steps, so that's not an option. So we need some other way of generating data that's relevant to these transitions. The classical solution has been what's called importance sampling, which is an unfortunately named term because I think it really doesn't do justice to the suite of methods that are available for sampling rare events. But it's basically the process of biasing the simulation in a systematic way so that we can generate data that's rare under the equilibrium statistics of the system and reweight it appropriately. But the problem with most, or essentially all, importance sampling techniques is that we have to define a reaction coordinate. We have to define some, external user-defined coordinate where I go in and I say, what I think is relevant is this distal histidine in the protein structure, and I'm going to bias that and see what happens, right? So I'm going to sample along a dihedral angle of this, one amino acid in this very large, complicated structure. And I think that's the thing that defines the reaction mechanism, and I'm going to look at that. So that of course is how much of biophysics is done, and it's a technique that can be very successful if you have a lot of mechanistic insight into the process that's occurring. The other thing that you can do, of course, is use something that's much coarser that you think might be correlated with the transition, but there's no guarantee that something like the root mean squared deviation from an initial structure to a target structure is actually going to provide a meaningful representation of a reaction coordinate. So this is a hard thing to design. It's a very challenging design problem. The other option is to focus on something like a Markov state model. So you do a Markov state model where you can observe transitions between many states, build a model, and then identify those states, do this spectral analysis where you look at the eigenvalues and the associated timescales with transitions. This is a hard thing to do as well because it also requires that you at some point observe these transitions, and that, as I was saying, can't always be guaranteed. So the problem is is complicated when you think about it in terms of proteins and complicated structures, but fundamentally it's kind of a simple problem to state. And the state is one of, or the problem is one of transitions between, two metastable basins. So ultimately what we want to do is characterize these transition paths between A and B. And A and B can be, states that are very close to experimentally determined structures. They're something that we know that are relevant to physical process. And there are two different perspectives on this. So the first is the one that I was just mentioning. It's this model that's based on Markov models. And there, what you're ultimately trying to do is find a spectral gap in some transition function. So you have a generator that you develop from a bunch of simulations. And then you look at the eigenvalues. You do some kind of clustering. You look at eigenvalues and the associated implied timescales for transitions between the states that you've identified. And that tells you about the different metastable states and the rate of interconverting between them. So that's a way of extracting rate information. But it's very sensitive to the clustering algorithm that you use. And that, in my opinion, is basically equivalent to the reaction coordinate problem. If you don't have a clustering method that identifies the slow kinetic degrees of freedom that dominate a reaction mechanism, you won't actually learn anything about the slowest processes in the system. The second is one that's based on transition path theory, or sometimes called potential theory, or transition path sampling. And that really tries to isolate the two basins A and B. So it says that there are two basins A and B. And what I want to do is study the statistics of transitions between A and B. So there are specific sampling methods like transition path sampling that have been developed for this purpose, but they can be quite hard to implement. So let's maybe go through a simple example just to discuss, what the right reaction coordinate would be in theory. So if I could construct the perfect reaction coordinate, what would it look like? Let's imagine Langevin dynamics. So I've written it here in discrete time with time step dt. It's just updating according to some potential energy, and then there's a noise term. So this is a Gaussian random variable where I have a diffusion that's proportional to my temperature, which is 1 over kVt. So this of course, has a well-defined steady state distribution. So if I sample this for a long time, what I end up with is samples from a Boltzmann distribution. That's the expression that's written here. So I have a Boltzmann distribution, and we can look at this quantity that's called a committer function. So the committer function is a conditional probability. It says that if I take a point along anywhere in the system and I ask, what is the probability? So the probability conditioned on X that I reach B, so the time of hitting the basin B is less than the time of hitting the basin A. So if I start, somewhere up here, what's the probability that I go to B before returning to A? Okay, so this function turns out to be basically the right notion for a reaction coordinate. If I could figure out what Q is, right, my committer function, and I could look at Q is equal to 1/2, that would be my transition state. That's a precise way of describing what the transition state is. It says that every point along Q is equal to 1/2 has equal probability of arriving in A or arriving in B. Right? So everything along there has equal probability of going from one basin or the other. That notion ends up being a really powerful one if you want to do some sort of importance sampling to describe the transition state, right? So if I wanted to figure out the reaction mechanism for some complicated process, if I could just sample along Q equals 1/2, then I would have a lot of insight into what's going on, because I would know, all of the states that end up reacting. Okay, so how do we actually find Q? So what's the right way of solving for Q? Well, the answer is kind of unfortunate. You have to solve a complicated PDE. So there's a high-dimensional partial differential equation. It's a partial differential equation that is in the same number of dimensions as your physical system. So if it's a protein, right, this might be a million-dimensional equation. And we can't numerically solve PDEs in dimensions greater than like 4, because you need to put it on a grid, and you typically need lots of grid points. So there aren't robust ways of doing this. In 1D, we could do this directly, right? So you can do this type of thing for really simple calculations, and you can write down an explicit expression for the committer. And you can check that it satisfies this PDE. And actually, it's kind of useful to look at a plot of it. So if you do this in 1D, and I've added a trivial degree of freedom in the other direction so that I get a 2D potential, then the committer is plotted as these contour lines. And basically what you see is that it, as you would expect, through the saddle point, it has probability 1/2, right? So you've basically localized information on the saddle point. So that tells you that that's where the transition state is. And then in all of this region, it's basically 1, because everything that starts over here ends up in B. And all of this region, it's basically 0, because everything that's over here essentially ends up in A. Okay, so they're well-defined boundary conditions. You can solve this PDE for a simple case, but that's not very useful for chemistry. So as I was saying, the imperfect solution here is to use a set of collective variables. So we could define some map that takes me from the high dimensional space of my protein, for example, into a very low dimensional space of 1 or 2 dihedral angles, and then I can sample by doing biasing in that space. But if I choose a bad reaction coordinate, I won't get any mechanistic information. So that's not the solution that I want to pursue. I want to see if we can do something different. So here's an idea. I told you that high dimensional functions are the one thing that you can represent with neural networks that you can't represent with other things. So can we try to represent the solution of this PDE using a neural network? Well, it actually turns out to be a pretty general problem. There are a lot of PDEs in chemistry, and we know various ways of solving them with basis functions primarily, although some of us know other ways of solving them as well. And there are these variational problems that pervade applications in physics and chemistry. So I'll just briefly describe. So this is a Ritz type variational problem where I have a Lagrangian L, and depending on the choice of Lagrangian, I can get a bunch of different types of PDEs that are relevant to physics and chemistry. So for example, if I wanted a Schrodinger equation, I would take something of this form, and the d mu would just be dx. If I want to solve the equation for the committer, then I end up with a different Lagrangian. So there's actually a class of functions that are relevant to StatMech, or a class of PDEs called backward Kolmogorov equations, where you can compute values of various averages that all fit in this form. And here the density associated with the system is a Boltzmann distribution. So in some sense, the statistical part of the Schrodinger equation is a bit simpler, though obviously the problem is very, very difficult. Okay, so we can take this variational perspective, and we can use a neural network ansatz within this variational formulation to try to represent the solution to this committer equation. So here's the basic procedure. I have a variational principle, and I have boundary conditions for it. So I know that Q is 0 for all points in A, the time of reaching A before B. So the probability of reaching B before A, if you're already in A, is 0. And for points in B, the probability of reaching B before returning to A is 1. So that's the set of boundary conditions, and I have a variational principle, and I know how to evaluate this variational objective. So all that I need to do is generate data, compute an estimate of this integral. Of course, I can't evaluate the integral analytically, but I can sample data from a Boltzmann distribution through molecular dynamics or Monte Carlo. I can plug it into this integral, and I can try to minimize on this, this cost function, and that will give me, as I optimize more and more, it will give me a better representation of the committer. That's the hope. So it only takes looking at this one-dimensional example to see why this is naive. The cost function here has two terms, right? So one is the gradient of Q squared, and the other is this Boltzmann distribution. So when I do molecular dynamics or Monte Carlo, what I end up with is samples in the most likely states under the Boltzmann distribution. So like on this potential, what I would see if I did sampling was that I would spend essentially all of my time in one of these wells, right? So wherever I've initialized, I would spend 100% of my time there. If this barrier is large, then the probability of observing a transition during the simulation is extremely low because it requires, an event that's exponentially unlikely. So there's no hope of sampling things where the gradient of Q is large, because the gradient of Q is large exactly at these points that are rare. So there's an issue with evaluating the objective, which is that you need extremely rare data to describe the transition state at all. So this naive approach of just doing molecular dynamics, evaluating this cost function, and running things is not going to work.
Grant,
Yeah.
we're down to about the last 5 minutes or so. Right?
Yeah, okay, so I'm actually getting close to the end,
Okay.
Believe it or not. Okay, so the basic idea is to do some sort of biased sampling, just like the importance sampling techniques. But what we're going to do is we're going to bias by an instantaneous value for the committer that I represent with a neural network. So I need to initialize this in some way. And then I'm going to sample along different values U, which are values that are related to how much progress along the reaction I have. And so in practice, we typically do something a bit simpler with this, which is that we add a Gaussian bias to bias the system. So this involves a type of reweighting. So this is really standard free energy calculation stuff in a way. Like anyone who's done a free energy calculation will be familiar with the methods that you do. You just use your favorite importance sampling method, and that gives you a way of biasing the system to evaluate this cost function. So you'll do an approximate evaluation of this cost function. That gives you something that you can actually optimize. Okay, so let's see how that works. So here's a simple example that is just taken because it kind of illustrates that the method is working. So this is a Moeller-Brown potential. It has a fairly complicated landscape actually for something in low dimension, and you can clearly see that the transition state is here. So I'm just going to show you an initial guess. So you can take as an initial guess just a line in high dimension or low dimension, right, between the two basins. You optimize a neural network along that, and then you're going to sample once you have that. So here's what the optimization dynamics actually looks like. So that's my initial representation of the committer. And as you run this optimization, so doing importance sampling at every step to evaluate the loss function and then taking a gradient of it, you get increasingly good representations and localization of the sampling at the interface. So this is something that actually works in this simple example. I like this example just because it's so visual, right? It makes it very clear that you've identified the right reaction state, the transition state correctly. So you can look at this from the perspective of the loss function. So you can actually evaluate this loss function. And what you see is that it does converge. There are still some transient fluctuations. If you really wanted to decrease these, you could decrease the time step or increase the amount of data. That would work perfectly well. Okay, so now for something a bit more non-trivial. So this is an Ising-like model. It's a continuous spins and a double well, and they're all coupled. So there's a lot of structure to this problem. And what we do is we put boundary conditions on it where there are positive spins at the right and left boundaries and negative spins at the top boundaries. So there are two metastable states. These boundary conditions lead to two metastable states where you have patches of plus spins on the right and left, or a whole filled in region of plus spins. So we can do this optimization procedure. It's harder to visualize in this case because this is now in 256 dimensions. And this is just showing what the loss does as a function of time. So because you start at this initial condition where you've done a linear interpolation, your loss is initially 0, but as soon as the spin system starts evolving, it jumps up. And this is just showing that, it's pretty robust. It converges consistently over a bunch of different realizations. And what you see is that if you sample transition paths for various values of Q, you can actually localize a fairly complex structure for the system, which is that we know from free energy calculations, which are much more expensive than the calculation that I'm doing here, that these transition paths pass through this characteristic hourglass shape. So this is the minimum free energy path. This is the most likely transition path for the system. And this is just showing that even in this very high dimensional space where, my input is, a spin system with 256 degrees of freedom, I can still learn a committer function that can bias the sampling towards these transition states very robustly. Okay, so I'll conclude just by bringing up one other interesting idea that we've started to look at more. So, I hope I've convinced you that one of the problems with trying to do these problems in the physical sciences is that often, the data that's relevant is very rare under the equilibrium statistics. So you can't just train models based on equilibrium MD. You need to do some important sampling on top of that to evaluate cost functions for interesting mechanistic things. So you could ask the question, well, can't we just use generative models to create the data? Like, can't we just sample a generative model and get new rare data? And I think there's reason to be optimistic about that because generative neural networks are capable of amazing things. So this is another example from OpenAI where they're using their model called DALL-E, which is a variant of GPT-3, and you can give it a text prompt to generate images that are sort of extremely complicated. I mean, it's really stunning to see what they can do with this. So you can ask for an armchair in the shape of an avocado and you get a bunch of pretty convincing, I mean, these are all completely generatives, right? So these are not real chairs. So that's kind of amazing. So the realizability of neural Monte Carlo involves a few constraints. You need invertible maps. That's the main thing. So you need neural networks that are actually invertible. So we use these things called normalizing flows, which you can ask me about later if you're interested in. And basically we have a simple procedure, which is that you generate samples, you train the normalizing flow, and you generate more samples. And so you can do this iteratively and build a better and better sampler in principle. And it works. So this is showing, a simple example where, as a function of time, so that your samples are the black curves. As you train the normalizing flow based on the data from the blue curves, you eventually, end up training something where the samples are actually coinciding with the underlying structure of the function. And this is something, so this example is nice because it illustrates that this is something that's robust on all length scales. So you can look at, the fluctuations at very small length scales in the system and see that you actually recapitulate them. But you can't really do the rare events problem, unfortunately. So we know even from really, really simple examples that you need to guide the sampling in some way in order to generate new or to generate things that are relevant for the metastable modes for the basins of the system. And that's something that you can see even with a one-dimensional example with a double well potential. So if you have two Gaussians and the Gaussians are far apart, if you initialize the sampling in one of them, that's where your training set is, you're never going to see the other one. So that's a fundamental problem. So let me conclude and just say, a bit more about, what I think neural networks have to offer us in chemistry and physics. So they're a very powerful tool for scientific computing. There's no doubt about that. But I think in general, we need to be very careful in the way that we think about both the data collection aspect for training neural networks and also, the specific architectures that we choose. So we in general want things that are over parameterized. We want things that have good initial conditions for training. And this is something that I don't think we need to just look to OpenAI and say like, wow, they're achieving amazing things. I think there's really a sort of developing fundamental understanding of what's going on that allows us to have some faith in these results. And the lesson is that over parameterization is really a feature of these things. So all of this asymptotic analysis was stuff that I did at NYU with a number of collaborators, Eric van den Eyden, John Bruna. And then recently with Eric and Andy Mitchell, who was actually at UCI as an undergrad, and Mary Lou Gabri, we've been looking at this committer calculation as well as some of the neural Monte Carlo type things. So using neural networks to generate Monte Carlo moves. Okay, so I'm happy to take any questions, and thanks again for having me.
Thank you, Grant. Maybe you can stop sharing for a minute, Grant.
Yep.
So we can just see everyone. And Dominguez, are you going to call out some of the questions? Something in the chat. Well, oh, Dominguez is muted. I'll read it.
Sorry about that. Yeah. How much does your method perform better than a supervised learning based reaction coordinates like the TICA or PCA?
Yeah, TICA. So we haven't actually compared systematically yet to TICA. This is something that we're working on now. My sense is that if we give the same amount of data to other methods and sample in precisely the same way, then I think the results will be probably indistinguishable. Where we have an advantage is that we can do this in an arbitrary number of dimensions. So if the the reaction coordinate that you learn with an unsupervised learning method has to be projected into a low number of dimensions as TICA requires, then the sampling that you do will be less robust than what we do. So I think that's where what we're doing is kind of fundamentally different from TICA, is that we can bias the system in a very high dimensional space so that we're sampling along transition states that are biased by the committer function itself rather than being biased by the dominant independent components that you get from a TICA type approach. But that's a good question. I mean, the comparison needs to be made. We haven't done it yet. It's just kind of early days.
It sounds like there must be complicated systems where people don't really know how to set them up that way, right? That would be the kind of one that you'd want to test on. Is that right, Brian? Yeah,
that's exactly right. So there are a lot of for example, drug binding type calculations where, the binding mechanism is a concerted process of, many degrees of freedom. And it can be extremely challenging to develop reaction coordinates for those sorts of things. So I think that's one context in which we'll definitely, try to make the case that these methods are superior to things where you have low dimensional reaction coordinates. And then, I think there's also just a conceptual advantage to using this type of approach in that you don't have to bias the system through, user knowledge. I mean, that can work in both ways, of course, right? There are cases where you might know something about the mechanism and want to use a low dimensional method. But if you don't know anything, then, choosing a low dimensional reaction coordinate can lead to results that are just wrong, right? And that's an issue too. So.
That question is from Demon Ray, by the way.
Okay.
And there are no more questions in the chat.
So maybe I can ask a few more. Yeah, so I think there may even be some fairly low dimensional cases where people sort of get it wrong, and they're interested not just in the sort of committer, right, but also the sort of shape in the vicinity of the committer, right? Because
yeah.
Sort of everybody assumes, well, none of that really matters, but in fact it does, right?
Yeah. So we're working on some systematic ways of actually spacing out the points along which we sample in order to localize things closer to the committer, because in many systems this region of transition states is kind of narrow, right? It's something that you need to sample well within that region, but almost everywhere else it doesn't really matter what you're doing because you're in the basin of attraction for one of the two metastable basins. And so every trajectory essentially ends up in one of those basins. So there's a very kind of narrow band of configurations where you're actually obtaining information about the reaction rate. So there are a lot of questions about how to space things out and how to sample well in those regions. Actually, I think a lot of this is also quite relevant for defining potential energy surfaces from DFT calculations. So, as we move to higher dimensional systems, yeah, right? The sample, you can't just systematically enumerate all of the geometries that you need in order to develop a potential energy surface, especially if you want to resolve parts that are involved in transitions, right? So you need high energy states, and you need a systematic way of developing those. So we've actually been thinking about applying some of these methods to those types of problems as well.
Hmm. And did I see that you need a sort of an initial, you have to start off with an initial guess for the network, right? And then you propagate, right? So that in that case, you could put in your TICA-like biases, as it were, and therefore, if they're useful, it'll refine them, right? But if they're not, I guess it will.
Yeah, it should find something else, hopefully. Yeah, so that I think is both an advantage and a limitation of the method. You do need some initial path to start the optimization, and if you have, so for example, in cases where you might have many reaction paths, this method will produce for you, samples that are localized to whichever one you start with. Maybe so this is also something that we're trying to investigate. It may be the case that if you have good sampling, so if you're doing something like parallel tempering for your importance sampling, then you can actually evaluate the objective function in many locations in space, and you'll actually capture some of those multiple paths. But that's that's something that definitely needs to be investigated as well.
Right. I guess there's a huge domain of applications of these methods, right?
Yeah. Yes.
Do we have any more questions? If not, let's thank Grant again.
Yes,
and,
thank you.
And Grant, I'll talk to you on Zoom.
Okay.
In a minute. Dominguez will cut us off.
Bye.
No. You want to stay a little bit and talk? I think he left.
Yeah, no, we'll talk on our own thing. Okay.
Okay.
Yeah.